This is my Calculus 1 course. Today we're going to continue to use the substitution rule to find the antiderivatives of expressions that are a little more complicated. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. Go ahead and get a screenshot of the differentiation formulas. You're going to need these throughout this class today if you don't already have those in your file. You're also going to we don't really need this, but this is technically the substitution rule. You can take a picture of that if you want. And you're definitely going to need these steps here. So make sure you have these steps in front of you if you don't want to have to memorize those. Now, before we continue, let's do some review on the chain rule because as we talked about in the previous class, we used the substitution rule in order to help us perform the chain rule in reverse. So you can kind of think of that, you can think of the substitution rule as using the chain rule in reverse. We have expressions that can be considered the result of finding the derivative of functions where we have to use the chain rule. So it's important for us to remember the chain rule and to understand it. So we're going to find the derivative, and the reason we have to use the chain rule is because we have an inside function and an outside function. Whenever you have that situation, you have to use the chain rule. So we're going to find the derivative of the outside function. That's step number one. So this green part is step number one of the chain rule, find the derivative of the outside function. Step number two, we're going to keep the inside function. So we already did step number two also. Step number three is we're going to find the derivative of the inside function and multiply it by everything we just wrote. So those are the three steps of the chain rule. And so you don't have to write this expression. You can just find the derivative and just write it. You really don't have to do these intermediate steps at all. But I'm just showing the process here. So there you go. That's about as simple as we can get when it comes to our final answer. So that is the chain rule. 3 steps. Let's try another problem. So again, we have a function inside another function. So if you want to try this one, you can go ahead and do it. See if you can remember the chain rule. Attempt this example, and when you come back, we'll do it together. Okay, we're back. So the first step of the chain rule is to find the derivative of the outside function. That's cosine. Second step is to keep the inside function. Don't do anything with the inside function. Third step is to multiply by the derivative of the inside function. And so we have cosine of negative 4x cubed times negative 12x squared. Now, just to avoid any ambiguity, we can put the negative 12x squared in front of the trigonometric function. It's probably better to do that. Now, you could keep it out, this product out here, or this expression out here, but it's best to really put it in front of the trigonometric function to avoid any confusion. We don't want to think that all this stuff is inside the trigonometric function. So if you got that right, excellent. That is the chain rule. So let's go to our first problems today. We're going to focus on a lot of problems that require differentiation formula number 10. This one up here, and also formula number 12, and we're also going to do problems that require formula number 13. So a lot of Euler's number problems and natural log problems. So we need to find the antiderivatives of this expression here. But if you look at this expression, you can see it's not exactly obvious what the antiderivatives are. So, in order to help us, we're going to use U substitution. It's called the substitution rule, but we use U as our new variable, so we often call it U substitution. So we're going to do what's called changing the variables. We're going to change from x's to u's to make this expression simpler so we can find the antiderivative. Now, U is almost always the inside function, but in this case it's not really going to be an inside function. It's just going to be natural log x. So you need to be aware that sometimes U is not going to be an inside function. Now, how did I know that U is going to be natural log x? Well, I don't. I'm just hoping that that's going to be the correct expression that we should define as U. If it doesn't work, then in step 5 the x's are not going to cancel out, and the resulting expression is not going to be integratable. We're not going to be able to find the antiderivative, so that would tell you that you chose the wrong U value, or the wrong expression for U. So now we're going to find the derivative of U, and we're going to write it with Leibniz notation. And remember, we do that for a reason, but it's not exactly obvious why. Now, the derivative of natural log x is 1 over x. How do we know that? Well, that is formula number 12. So you should have those formulas in front of you. We also need to write the ornament dx. Now, dx is an ornament. It's not a real variable. It's a pseudo-variable, but du is a real thing. So we write the dx because it's just something that helps us change variables. So we're going to solve for the ornament dx. And we get x times du is equal to dx. That's step number 3. Step number 4 is to rewrite the integral. We're going to replace natural log x with u, and we're going to replace dx, this ornament here, we're going to replace that with what we found dx to be down here. Step 5 is to cancel out the x's, and if we did this wrong, then the x's would not cancel out. If we chose the wrong value for u, or the wrong expression, the x's would not cancel out, or something strange would happen. Okay, so now, do you agree that finding the antiderivative of u is a lot easier than finding the antiderivative of natural log x over x? Now, du is not an ornament, it's an actual thing, but we can pretend that it is an ornament because when we use the chain rule in reverse, the derivative of the inside function disappears. We're going backwards. If h of x is equal to some function within another function, then the derivative, according to the chain rule, is the derivative of the outside function, and we keep the inside function, and then we multiply by the derivative of the inside function, g prime of x. But if we were to go backwards, finding the antiderivative, then this yellow g prime of x would disappear. So we almost don't even have to consider it to be there. That's why the du disappears. And we can just consider the du to be an ornament because it doesn't really affect, the antiderivative, or how we find the antiderivative, at least in our minds. So step 6 is actually to find the antiderivative of u, and that's just u to the second power, because this is a first power. If we want to find the antiderivative, we add 1 to the exponent, and then we ask 2 times what is equal to 1, because when we find the derivative of this and go backwards, we're going to have to use the power rule, bring that down, and if we multiply it into 1/2, we get 1, so we get the original expression. So you've done this many, many times before in previous classes, finding the antiderivative of x. What is the antiderivative of x? Well, that's just 1/2 x squared, if you recall from previous classes, so that's what we're doing here. Okay, so step number 7, last step, is to replace u with what we said u is equal to, and that's natural log x. So that is the answer. Now, how do we know that this is correct? Well, we could always check it. We'll find the derivative of this blue expression and see if we get the yellow expression. So if we find the derivative of this, we have to use the chain rule. remember, we're using the chain rule in reverse to go from here to here, but if we have to use the chain rule going forward to check our answer. So we have a function within another function. So we have to use the chain rule. So we're going to find the derivative of the outside function. So we're going to bring that 2 down and subtract 1. So that was the derivative of the outside function. We're going to keep the inside function, and then we're going to multiply by the derivative of the inside function, but the derivative of natural log x is 1 over x. Remember, we talked about that over here. So notice that these 2's cancel out, the 1/2 and the 2, and we get natural log x to the 1 power times 1 over x, and that equals what we started with, natural log x over x, if we put those together. So these are just some more examples of problems that require the substitution rule. So we want to find the antiderivative of this expression, but we don't know what to do. This is a complicated expression. Now remember, the derivative of e to the x is e to the x. It's the only function whose derivative is equal to the exact same function. So we're going to use u substitution, and u is usually going to be the inside function. In this case up here it wasn't, but in this case it looks like it's going to be e to the x. So step 2 is to find the derivative of e to the x, and that's just e to the x, but we're going to write the ornament next to it. You always write this pseudo variable next to your derivative, because that helps us to change the form of this integral. So then we're going to solve for the ornament. That's why we write the ornament, is we're going to solve for it. And in step 4, we're going to rewrite the integral, but we're going to replace e to the x with u. Now, in this case, things are kind of a little confusing. We're also going to replace dx with what we said dx is equal to here. Now, we said that we're going to replace e to the x with u, right? Well, that means that this e to the x could also be u. So a lot of students might get kind of confused by that, but if you make this e to the x u, then you won't see that this green e to the x cancels out. You could make both of these e to the x's u, and then the u would cancel out. But however you want to do it, we need to find an expression that helps us to find the antiderivative. So sometimes things can get kind of confusing with substitution, to be honest with you. Well, now we have an expression that's much easier to integrate. We can find the antiderivative of this much easier than we can find the antiderivative of that expression up there. So step 6 is to find the antiderivative, and that's just going to be sine u. And step 7, the last step, is we're going to replace u with what we said u is equal to, and that's e to the x. So that is the antiderivative, and you can write parentheses. Probably best to write parentheses there just to avoid any confusion. So I'd encourage you to use the chain rule and find the derivative of this expression, and you'll see you get back to this green expression up here. If you use the chain rule, you have to find the derivative of the outside function, so that would be cosine. Second step is to keep the inside function, and the third step is to multiply by the derivative of the inside function, but the derivative of the inside function is e to the x, because the derivative of e to the x is e to the x. And then it's typical to put this in front, and you see we have the same expression that we started with. Okay, so let's try a couple more of these before you try one on your own. Now, this is kind of a trick problem. This is a really tricky problem. I don't like giving you these types of problems, so I'm probably not going to give you one like this without warning you about the trick. The trick is we need to change tangent to sine x over cosine x. That's a trigonometric identity. We have to use that trigonometric identity in order to find the antiderivative of tangent x. If you don't use this trigonometric identity, we can't really find the antiderivative. So sometimes, I just want you to be aware, sometimes you're going to be expected to use trigonometric identities to kind of play around and see what you can do to help you find the antiderivative. And that's not fair for students to have to just somehow figure that out, but unfortunately these types of problems are in textbooks all over the place. So if you can't figure out what to do, you try using trigonometric identities or changing the form of the expression in some way, as we did in previous classes, so we can integrate. So u is actually going to be cosine x. If you tried to make sine x equal to u, you would find that you would encounter some problems. So we're going to do the same thing that we did on the other problems, same steps, finding the derivative in the second step. Solving for dx, the ornament, in the third step. In the fourth step, we're going to rewrite the integral, but instead of cosine x, we're going to write u, and we're just going to keep that sine x for now, and instead of dx, we're going to write what we found dx to be down here, even though dx, again, is not a real thing. We say we found dx to be something, but dx isn't anything. It's not going to be anything. It's just a pretend variable, so to speak, or a pretend value that helps us to change variables. So now on step 5, we're going to cancel out the x's, and it turns out the negatives cancel out also, so we have 1 over u du. Now just be aware that a lot of people like to write the du up in the numerator, and I think that's not a good thing, because that kind of distracts from the idea that it's supposed to be considered an ornament, even though du is not an ornament. Again, dx is an ornament, du is not an ornament, but we can pretend that du is an ornament to find the antiderivative. Now a lot of students would look at this and they would say, well, we have to change this to u to the negative 1, and then we have to add 1 to the exponent, but what you find if you do that is you get 0 in the exponent, and students get stuck. So in the rare situation where you have 1 over u to the first power, you have to remember your differentiation formula number 12. If you have this expression, the antiderivative is going to be natural log x, because the derivative of natural log x is 1 over x. So the antiderivative of 1 over u is natural log u. Okay, so now in step 7, we're going to replace u with what we said u is equal to, that's cosine. And there you go, that is the antiderivative. So if you want to find the derivative of the natural log of some function, you have to use differentiation formula number 13. If you want to check your answer, that is. So the derivative of the natural log of some function g of x is just the derivative of that function divided by the function itself. That's kind of a weird rule. So if we find the derivative, just to check our answer, the derivative of the inside function is negative sine x, and then we divide by the inside function, but sine x over cosine x is tangent, so we have negative tangent, the original expression there. Okay, so let's try one more of these. Again, notice that we have a lot of natural logs and e to the x's, and we're focusing on that with this first problem set. So you can see that this expression is really nasty. It doesn't look like it's going to be very easy to find the antiderivative of that expression. but let's use U substitution to try to simplify this expression. We're going to let U be the inside function. That's normally what it's going to be. And before we find the derivative, we're going to need to change to 1/3 power. Now we can find the derivative. We have 1/3 times x to the negative 2/3 using the power rule, and we can't forget to write our ornament. And now, before we solve for the ornament, I'm going to rewrite this expression. And I think we'll go up here for step number 3. We're going to solve for the ornament, and we get 3 du times x to the 2/3 is equal to dx. So in step 4, we're going to rewrite that integral, but we're going to try to change variables. So we have e to the u over 6 times the cube root of x squared. Then we have to replace dx with what our expression is equal to up here. So we have 3 times du x to the 2/3 power. Now notice that x to the 2/3 power is the same thing as the cube root of x squared, based on exponent rule number 10. So these expressions are going to cancel out, and the 3 and the 6, that's going to become 1/2. And we're going to have, looks like e to the u du. So this expression is a lot easier to find the antiderivative of than this expression. The derivative of e to the u is just e to the u. So the antiderivative would just be e to the u. And then of course we can't forget our 1/2. And lastly, we're going to replace u, what we set u equal to, which is the cube root of x So there you go. That is the family of antiderivatives of this this function. So go ahead and take a picture of these problems. I'm going to give you one more chance to take a picture of these differentiation formulas and this information here. And I want you to attempt number 5. Now it says you need to use a differentiation formula number 12. So number 12 is this one here. The derivative of natural log x is 1 over x. So be ready to use that formula. And usually u is going to be the inside function. So just to get you started off today, I'm going to tell you what u is. I'm going to tell you what u is going to be. If you choose the wrong u, that's okay. It's just on step number 5, the x's may not cancel out. So u is going to be natural log x. Okay, so I want you to get started on the right foot today. So make a u natural log x, follow your steps. Again, I'm going to give you one more chance to take a picture of these steps. You have to follow these steps and get started with number 5 and see what you can do. When you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. Go ahead and try problem number 6, but be aware that you need to use differentiation rule number 10. And you need to use the chain rule because we have a function inside another function. Now, a lot of students have trouble using the chain rule when they're finding the derivative of something like this. The outside function is e, the inside function is this. So it's kind of a difficult thing for the mind to understand exactly how to use the chain rule, but see what you can do, and if you get stuck, that's okay. But we're going to, and by the way, if you haven't got a picture of these problems may help you. Go ahead and try number 6. And again, if you get stuck, that's okay, but give it an honest attempt. When you come back, we'll do it together. Okay, we're back. If you got that right, excellent. I want you to try number 7. Now, usually u, like I said, is the inside function. But in this problem, u will not be the inside function. Okay, so you can see over here, I'm giving you a hint. I'm actually telling you what u is equal to. It's not always the inside function. It could be something else. It's usually the inside function, but not always. So try number 7. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Now again, you need to practice differentiation formula number 13. If you're having trouble with that, you need to practice that. You can go back to my earlier classes and practice differentiation formula number 13 if you need to. So again, I would encourage you to find the derivative of this expression using the chain rule, because we have a function inside another function. I would encourage you to use the chain rule and see if we get back to the original expression, and you see that we will. Okay, so I want you to try number 8. Remember, the derivative of e to the x is e to the x. And use your differentiation formulas. Try number 8. When you come back, we'll do it together. Okay, we're back. If you got that right, perfect. Okay. So let's do this next one together. This is just another version of one of these problems. We can see that this is really complicated. How do we find the antiderivative of that? It's really not something that looks very easy. But you might have to use some trial and error here. We don't know what u is going to be equal to. We don't know exactly what the inside function is. But in this case, it's going to be the denominator. Now, how do you know it's the denominator? You don't. You can try the numerator, but if you do that, then on step 5, you're going to start to observe some problems. The x's probably are not going to cancel out. So let's go on to step number 2, find the derivative of that expression. Now, here's where kind of a strange situation happens. Oftentimes, you'll see dx written here. And again, dx doesn't exist. It's an ornament. It's not a real thing. It's a pseudo expression, pseudo variable, pseudo notation. But we're assuming that dx is multiplied by all this. But oftentimes you won't see parentheses. Oftentimes they'll just be left off. And that's because people are kind of caught in between the concept of believing that dx is real and believing that it's not real. But in order to indicate that this is multiplication, I'm just going to write parentheses because I don't want to make things any more confusing than they already are. So we're pretending that dx is really multiplied into that, even though dx it's non-existent, so it's not really multiplied into anything. But in order to do the process here that we need to do to change variables, we need to pretend that it's that expression is multiplied by dx. But just keep in mind that sometimes you will not see parentheses, and that's very confusing. Okay, on to step 4. So we're going to rewrite the integral, and u was the denominator, if you recall. And we're going to replace dx with what we have down here for dx. So that's du over 3x squared plus 8x minus 1. Okay. So now we're stuck. There's nothing that we can do. The x's don't seem to be canceling out, but they actually will cancel out. Do you have any ideas how we can make the x's cancel out? What we can do is we can actually factor out a 5 out of this thing. So I want you to be aware that sometimes you need to do that. You're going to need to do that in the next problem. So I'm going to factor out 5, and then I get 3x squared plus 8x minus 1, which is exactly the same as the expression we have down here. So math can get tricky like that, and you just need to be aware that that type of thing happens. So now you can see that this expression cancels out, and that's what we want. We know we did this correctly now that the x's cancel out. So we have 5 times 1 over u du. Now this is where a lot of students would have more problems, because they would look at this and they would not integrate properly. You can't simply change this to u to the negative 1 and think you're going to find the antiderivative, because you're going to come across some big problems. When you add 1, you get u to the 0 power. Well, that doesn't really do anything, right? You have to remember that the antiderivative of 1 over u is natural log u. That's one of those differentiation formulas. I forget which one. Now we're ready to do step number 7. So we have 5 times natural log, and we need to plug in what we defined u to be. So that's the answer. So this is just one more of the many types of problems that you can get where we have to find the antiderivative of an expression that seems fairly complicated. So I'd encourage you to find the derivative of that expression. When you find the derivative of the natural log of a function, the derivative is the derivative of the inside function divided by the inside function. And you'll get this exactly. So number 10 is very similar to the problem we just did. So I want you to try number 10. Again, you must use differentiation formula number 13. And you also have to use differentiation formula number 12. So I should mention that also. So while I write that in, go ahead and try number 10. And when you come back, we'll do it together. Okay, we're back. And so there we go. So again, I would encourage you to find the derivative of this expression and check your answer. But if you got that right, excellent. Now remember, you have to factor out 2. So if you got confused by that, that's okay. But now you know you have to factor out that 2 so you can cancel out the x minus 5. So again, be aware, these are problems where we had this situation where we had to write parentheses because we're pretending that we're multiplying dx, even though dx doesn't really exist. But again, a lot of times you're not going to see those parentheses. The dx is just going to be written right next to the expression, and that's kind of confusing. So here we're going to encounter a similar situation, but it's going to be a little different. You'll see why. So we don't know exactly how to find the antiderivative of this expression, but we'll set u equal to x minus 1 and find the derivative, and the derivative of x minus 1 is just 1. but you don't really have to write one. You can just write du is equal to dx. So this is a case where the derivative of u is just going to be considered to be equal to dx. And so in step 3, we don't really have anything to do. Dx is already solved for. In step 4, we're going to, again, change to a u integral. Now dx is du, so we just place it with du. So be aware that that sometimes can happen. And so step number 5 is not really necessary either. There's no x's to cancel out. Sometimes there's no x's to cancel out. So be aware of that. Make a mental note of that. Sometimes there are no x's. So that's good. That means we don't have to worry about those x's. And we really should probably rewrite this just to make it easier to find the antiderivative, or just to identify what is going on. So we have a 1 over u. Remember, whenever you have a 1 over u, the antiderivative of that expression is natural log u. That's something that's hard for students to remember. You either remember it or you don't. But if you do remember it, then you can find the answer really easily. So we made u x minus 1, and there we go. That is the antiderivative, or the family of antiderivatives of this expression. So I want you to try a problem like that. So you're going to find that du is equal to dx in your problem. So go and attempt number 12, and you're going to need a differentiation formula number 12. So see what you can do. When you come back, we'll do it together. Okay, we're back. So there you go. If you got that right, excellent. Okay, so in the previous problems, we found a family of functions because we were trying to calculate indefinite integrals. But remember, if you have these numbers here, we're trying to find the value of a definite integral as opposed to an indefinite integral. And a definite integral is a number. It's not a family of functions. So now we're actually looking for a number, and we're just going to do the same thing we did before. We're going to use substitution to find the value of this definite integral. So we're going to find the antiderivative, but then we're going to use the fundamental theorem of calculus to find the value of the integral. Now you can see that this is a complicated expression. That's why we need to use substitution. So step 1, what are we going to make u? Well, u is usually the inside function, and it might be good to rewrite this integral in a way that's easier to understand. So if we use parentheses, we can see what's going on, because many students get confused by this 8 being here. But this is what that actually means. So u is going to be the inside function, and du is cosine x. Don't forget to write your ornament, your pseudo variable dx. And then we're going to solve for dx as usual. And in step 4, we're going to replace the integral with a du integral. And I'm not going to write the limits of integration. I'm not going to write them on this integral. All I'm going to do is find the family of antiderivative functions, and then I'm going to use that later on to actually find the value of this integral. And the reason I'm going to do it that way is because we can't use the same limits of integration if we change to a different variable. If we change from what we call a dx variable, or excuse me, if we change from what we call a dx integral to a du integral, meaning from x's to u's, we can't use the same limits of integration because these limits are x values. these yellow limits over here are x values. If you change to a du integral, then your limits of integration have to be u values, not x values. So you'd have to actually change the numbers. And changing the numbers is not that difficult. It's just that it introduces more complications. So we're not going to do that. We're just not going to write the limits of integration right now. We're just finding the family of antiderivative functions. So I'm going to replace sine with u, and then I'm going to replace dx with what we have over here. So I'm going to take that dx, and I'm going to replace it with what we have down here. So du over cosine x. The cosine x's are going to cancel out in step 5. And so we have the integral u to the 8th power times du. And even though du is not really an ornament, we can pretend that it is an ornament because it's going to go away. So now we can find the antiderivative, which is 1/9 u to the 9th plus c. And in step 7, which is usually considered to be the last step, we replace u with what we made u equal to. That's sine x. So normally we'd be done at this point. We found the family of antiderivative functions, but the problem is we're trying to find the value of a definite integral. So our answer should be just a number, not a family of functions. So now what we're going to do is I'm going to change to a different color here, and I'm going to go to what we're going to call step 8. And step 8 is actually going to be finding the value of this integral using the fundamental theorem of calculus. So let me change that. So remember, if we're going to use the fundamental theorem of calculus, we have to find the antiderivative, or the family of antiderivative functions, but we have that up here. Now, remember, we have that abbreviated way to write this, and that the abbreviated way doesn't use c's. The c's are always going to cancel out. So we don't really need to write c, but I'm just going to do it that way this time so you can remember how the fundamental theorem of calculus works. So we're going to write this antiderivative family of functions, but we're going to plug in pi over 2. And then we're going to subtract that same family of antiderivative functions, but now we're going to plug in 0. So you can think of it as the antiderivative function with pi over 2 plugged in minus the same antiderivative function with 0 plugged in. So there you go. So I know that this is kind of confusing, but that's just sine pi over 2, and then you, whatever that ends up being, you raise it to the 9th power. So you don't have to do this, but if that's kind of confusing you, you can change it to this, and then you'll understand exactly what's going on. You see how we changed that? It makes it a little easier to see what this expression means. Okay, so let's double check everything. Make sure we did everything correctly. When you're doing a math problem, you always want to go back and double check over and over and over again, because you're going to waste a lot of time if you just rush forward, because it's almost a guarantee that we'll make at least one mistake. It's just the nature of the human mind. Okay, now we need to obviously find sine pi over 2, but how in the world are we going to do that? Well, at this point in the math curriculum, you're expected to know how to do that. Now, if you're finding a sine of like a 60-degree angle, or maybe 240 degrees, which would be over here, or maybe sine 135 degrees, which would be here, then you would use a triangle. But if you have a quadrantal angle, which is a multiple of 90, or possibly 0, the triangles collapse. So in that situation, you can't use triangles. You have to use the sine graph, which is this. So we have 0, we have pi over 2, pi, 3 pi over 2, and 2 pi. Now, if you don't remember what the radian units mean in terms of degrees, remember pi always represents 180, so 180 divided by 2 is 90 degrees. So 90 degrees would be right here, pi over 2. And of course, the value of that is positive 1. Okay. So sine pi over 2 is positive 1. And by the way, sine 0 is 0. And maybe I'll just keep that graph over there. So 1/9 times 1 to the 9th power plus c minus, and maybe before I actually find those values, I'll just distribute the negative just to go slow here. So we have minus 1/9 sine 0 to the 9th minus c. So you can see why writing the c's is kind of a waste of time, because they're always going to cancel out. So now we have 1/9 times 1 to the 9th power. The c's cancel out. And we have minus 1/9 times 0 to the 9th power, because sine 0 is 0. And then of course this just becomes 0, and this becomes 1. 1 to the 9th power is 1 times 1/9 is 1/9. So there you go. Now if you were to graph this function, it would probably look fairly complicated. And so what area exactly are we finding? That's not exactly clear, but you don't have to know that. We're just finding the value of the integral. So there you go. That was finding the value of a definite integral when we had to use the substitution rule. So on to number 14. Again, first we didn't write the limits of integration. We just left those off. We didn't write those here. We found the antiderivative functions, and then we rewrote the definite integral and actually figured out what the value is using the fundamental theorem of calculus. Okay, so we're going to do the same thing again. Now notice we have a dx in the numerator. What in the world is going on there? Well, it's not really appropriate to write the dx up there, but a lot of mathematicians like to do that. It's an ornament, so it shouldn't really be in the numerator of a fraction. It should be over here, and you should have a 1 there. But because so many mathematicians do that, I'm gonna write it that way, or I'm showing you that way, because it's very possible that you could see that, and I don't want you to be confused. Okay, so this is what it really means. Okay, so obviously this is a complicated expression. We don't know how to find the antiderivative of that, but we can use our substitution method to help us. So step 1, as usual, is to figure out what u is going to be, and u is almost always the inside function. It's not always the inside function, but most of the time it is. If we find the derivative, we get negative 5 dx. Derivative of 1 minus 5x is negative 5. And then if we solve for the ornament dx, we get negative du over 5. And so now we're going to replace our dx integral with a du integral. So we have And we're not going to write the limits of integration. So we have 1 over the cube root of u to the 7th power, and then we're going to replace dx with what we found for dx over there, so we get negative du over 5. And in step 5 we're going to cancel out the x's, but in this case you can see there are no x's, so we didn't really have to do much for that step. But we can change the form of the expression a little bit to help us find the antiderivative. Now, what does this turn into here? Well, this is u to the 7/3 power by the by exponent rule number 10. And by exponent rule number 8, we can bring that up, so it becomes u to the negative 7/3 power. So all of that turned into that. It just makes it look nice and neat, and we can organize things. Okay, so now we're ready to find the antiderivative, so we add 1 to the exponent as usual, so we get negative 4/3. And when we find the derivative, to check our answer, we need to get a negative 1/5 here, so negative 4/3 is going to be brought down and multiplied into something to get negative 1/5. So what is that something going to be? Well, it looks like it's going to be 3 over 20 if we solve for x. And that is our antiderivative. So you always want to check to find the derivative of this and make sure we got that right. And it looks like we did. So now in step 7, finally, we're going to go back to x's, and we're going to replace u with 1 minus 5x. But remember, we don't really know what that means, and this is a perfect example of why we don't want to keep our answers with negative fraction exponents, because when we plug in our limits of integration using the fundamental theorem of calculus, we're not going to know what this even means. So that's why we have to write the family of antiderivatives without negative fraction exponents. So that's going to come down and become the cube root of 1 minus 5x to the 4th power. Okay. So that is the family of antiderivatives, and now we're ready to go on to step 8. So I'm going to copy this. And bring it down. And so we have the family of antiderivative functions. So now we just use the fundamental theorem of calculus, but I'm not going to do it the way I did before. You see how we wrote the blue C's? I'm not going to do it that way, because it's just not the way that it's done. When you learn the fundamental theorem of calculus, we just don't use that anymore. There's no point in continually writing C values over and over again when we know they're just going to cancel out. So what we do is we write 3 over 20 times 1 over the cube root of 1 minus 5x to the 4th power, and then we write a bracket, and negative 5 and negative 4 are limits of integration, and that tells us how to use the fundamental theorem of calculus. So now all we have to do is just write this expression with negative 4 plugged in, and subtract this expression with negative 5 plugged in, this whole thing. So we have 3 over 20 times 1 over the cube root of 1 minus 5 times negative 4, and that's all raised to the 4th power. And then we're going to subtract 3 over 20 times 1 over the cube root of 1 minus 5 times negative 5, and all that's going to be raised to the 4th power again. So I'm going to bring this over here. Obviously there's not much room, but you probably want to write an arrow so we know we're shifting over there. Okay, so let's double check, make sure we did all this correctly. There's a lot of stuff we're writing here, so I want to make sure. And so we don't have a lot of room to write this, but this is going to be negative 20, and it's a double negative, so it's 1 minus negative 20, so that's 1 plus 20, so that's 21. So we have 3 over 20 times the cube root of 21 to the 4th power, and that's going to be a hard number to calculate. So we're not going to calculate it. We're just going to write the exact answer and just leave it. You could find a decimal approximation if you wanted to, but I don't really care what the decimal approximation is. We only care that we can find the answer. So now we have 25 plus 1 is 26, so we have the cube root of 26 to the 4th power. And there you go, that is the final answer. So if you want to find a decimal approximation, you can do that, but we don't really need to. Okay, so there's another example where we use the substitution rule for finding the value of a definite integral. And remember, again, when dx is in the numerator, you can just put it off to the side and replace it with 1. So let's do one more of these before you try one on your own. These are really important problems, so we're going to find the antiderivative of this expression so we can use the fundamental theorem of calculus to find the value of this integral. But this is a complicated expression. We don't really know how to find the antiderivative, so we're going to use u substitution, and u is typically going to be the inside function, which is obviously this function here. So that's step 1. Now step 2 is to find the derivative, but we can't find the derivative because we don't know how to deal with 1 over x squared. We could use the quotient rule, but most students don't really want to do that, so you can change it to x to the negative 2 power. So step 2, we're going to find the derivative, and that's going to be negative 2x to the negative 3rd power, and we have to write our ornament just because it helps us change variables. So now we have negative du over 2, and you know what, before we even do that, I'm sorry, it's going to be a lot easier to understand what's happening here if we change the form of this to 2 over x cubed. Negative 2 over x cubed. So now we're going to multiply both sides by negative x cubed, and we get negative du x cubed, and we're going to divide both sides by 2. And we solved for our ornament. Okay. So now we're going to go to our integral, and we're going to replace it with a du integral. So we're going to replace 9 plus 1 over x squared with u, and we're going to replace dx with what this says dx is equal to. So that's negative du x cubed over 2. And if we did this correctly, our x cubes should cancel out. And they do. So we get the integral of 1/2, or negative 1/2, u to the 4th power du. Now again, du is not an ornament, it's an actual thing, which is different from dx, which is not a thing. But we're pretending that du is not a thing. Also, we're pretending that it's an ornament just like dx, because it disappears based on the logic of using the chain rule in reverse. When you use the chain rule, you multiply by the derivative of the inside function. But when you go backwards, the derivative of the inside function just disappears. So we canceled out the x's in step 5. And in step 6, we're going to find the antiderivative. So we're going to add 1 to the exponent. And it looks like we're going to have negative 1/10 here. Now find the derivative of that expression, and you should get back to this expression here. You always need to check. Okay, and then step 7, we're going to go back to an expression with x's. We made u 9 plus 1 over x squared. So that is the antiderivative, or the family of antiderivative functions for this expression. Okay, so now we're ready to find the actual value of this definite integral. Remember, a definite integral is a number. We're looking for a number. So we're going to step number 8. And to differentiate between all the other steps, I'm going to use a different color. So again, if we want to find the value of this integral, we use the fundamental theorem. And we don't really care what the graph looks like. The integral might be 0, it might be negative, it might be positive. We don't really care. Right now we're just learning how to find the values of definite integrals using substitution. So again, I'm not going to do it the slow way where we write the c value. I'm going to write it the way where we draw brackets. And what this tells us is we write this function without the c value, because c is going to cancel out anyway. We write this with 3 plugged in, and then we subtract this same expression with 2 plugged in, and that's the value of the integral. Again, that's the fundamental theorem of calculus. Okay, so let's make sure we got that right. Everything looks correct. So we're going to plug in 3. And then we're going to subtract the same expression with 2 plugged in. And we're going to make sure that we have all that right. We need another parenthesis there. There's a lot of parentheses involved here, so we need to double check. Looks like everything is correct. So we have negative 1/10 times 9 plus 1 over 9 to the 5th power, plus we got a double negative, 1 over 10 times 9 plus 1/4 to the 5th power. So that's all we're going to do. That's all we really need to do. That's the exact answer. But if we start trying to raise things to the fifth power, we're going to get some difficult numbers to deal with. So I don't really require you to go any further. Usually we want to simplify our answers as much as we can, but this is really as much as we can simplify. If we went any further, it would just be a lot of work for not much benefit. Okay, so I'm going to have you take a picture of these problems here, and I'm going to leave number 15 in the window, and I want you to try number 16. So remember, you want to find the family of antiderivatives first, and then go to step 8 and actually use the fundamental theorem of calculus. So go ahead and try number 16. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. If you haven't already, I want you to get a picture of these two problems and the two problems that we just did. And I want you to try 17. Now remember, if you have a dx in the numerator in your expression, don't be confused by that. You can put the dx off to the side like this and just make that a 1. So go ahead and try number 17, and when you come back, we'll do it together. Alright, we're back. So there you go. Now, you may have written this in a different form. If you want to, you can rationalize its denominator and multiply both sides by root 10. Then you should have 2 root 10 over 90. And you can reduce that to root 10 over 45. So you may write it in different ways. Now, you might say, well, you can't leave the root there. You're supposed to rationalize the denominators. And that is true that oftentimes you'll see that. And you can do that if you want to, but the purpose of this is really just to learn calculus. As long as you got the answer, then that's fine. Now, you could also get a common denominator. If you multiply both sides of this fraction by root 10, you could find a common denominator. You could probably simplify this quite a bit, but we don't have enough room on the paper, and we don't really care one way or the other at this point. But you do need to know how to change the form of this expression. If you look in the back of a calculus textbook and you want to look at the answer and see if you got it right, well, how are you going to do that? Unless you know how to change the form of this, or at least put it in decimal form. That's one way to check your answer. You write this in decimal form and then write the answer in the back of a textbook if you're using a textbook in decimal form, and then you can check to see if you got the right answer. So the reason I'm mentioning textbooks is because that's why you have to know how to put this in different forms to check to see if you got the right answer. Again, that's the name of the game when it comes to school, math courses in school. So that's one of the many reasons that you have to do that. So I want you to try number 18. So we have the same situation, a definite integral, but this expression is really complicated. So we need to find the antiderivative to use the fundamental theorem of calculus. Problem number 13 is going to be very helpful for you when you do that. So try 18. When you come back, we'll do it together. Okay, we're back. So what would that look like on a graph? We don't care right now. We're just using the substitution rule to figure out how to find the values of definite intervals. So if you got that right, excellent. And we should probably extend that out. So that is the cosine x curve, by the way. And over here it goes down like so. I didn't draw it perfectly, but so 3 pi and pi, that's negative 540, I believe, or something like that, and negative 180. So those are quadrantal angles. Okay, so now we're going to do some more challenging problems. We have a complicated expression here. We don't know how to find the antiderivative. And so we are going to use the substitution rule, but we're going to encounter a problem on step number 5. And it's going to seem that we're stuck. But sometimes the substitution rule can be salvaged. So let's demonstrate. We're going to find the antiderivatives of this. We don't have a definite integral. This is indefinite because we have no limits of integration. So as usual, u is going to be the inside function. And in step u, we find the derivative, and in this case, du is just going to be equal to dx, because the derivative of 6 plus x is just 1, right? So in step 3, we're going to solve for dx, but we already did that in step 2, so it's not really necessary. And then in step 4, we're going to rewrite the integral, but we're going to write it as a du integral rather than a dx integral. So we have x over u to the 8th power, and then instead of dx, we're going to write what this equation tells us dx is equal to, which is just du. So in step 5, we're going to cancel out the x's, but they're not canceling out. So we have a big problem here. So at this point, because x's are not canceling out, usually what we would do is we would just go back and say, well, let's choose a different value for u, or a different expression for u in the integral. The problem is, what else is there? You could let x equal u, but that would just be the same integral. It wouldn't be any easier to find the antiderivatives. There's really nothing else we can do. There's no other option. We could try making this whole expression here equal to u, but that wouldn't really help us. It wouldn't make it easier to find the antiderivatives. So at this point, it seems like substitution has failed us. We don't really know what to do. But we're going to do something different. I'm going to write this in purple, because if you look at your steps for using the substitution rule, on step number 5, you see the purple writing there? It says if the original variable, usually x, does not cancel, then you may need to set u equal to a different expression in the integral, or solve for x. So this is what we need to do. We need to solve for x in the equation defining u and replace the x variables in the integral with the expression for x in terms of u. What in the world does that stuff mean? Well, it's kind of tricky, so let's demonstrate. You don't encounter these types of problems as often, but you will see them. It's a guarantee, pretty much. What we need to do is we need to, I'm going to rewrite this equation over there just so we see where that comes from. You see that? I'm rewriting that. And then I'm going to solve for x. So I'm going to subtract 6 from both sides, and now x is equal to u minus 6, right? Well, now I'm going to do step 5, but I'm going to replace x. So we already have u to the 8th in the denominator, and we have du, right? But I'm going to replace x with u minus 6. So now, instead of this integral up here, we have this integral. So the question is, how did that help us? And a lot of students would say it didn't help us at all. But actually, it did. Believe it or not, we really cannot integrate this yellow expression over here very easily. But this expression, we can integrate. All we have to do is just change the form. When you divide a sum or a difference by some term, you can just use what we call fraction decomposition, or you can just divide each term by that term in the denominator. So each term gets divided by u to the 8th. That's just basic mathematics. You need to understand that that's just basic mathematics. A lot of students see this and they get really confused, but we learned that all the way back in beginning algebra. So now we're going to use the basic exponent rules. Now you see this green 1 there? If a variable doesn't have an exponent, it's assumed to be 1, right? So now we're going to use exponent rule number 2 and just subtract the exponents. So 1 minus 8 is u to the negative 7th. And we're going to use exponent rule number 8 because we can't find the antiderivative of this without bringing that 8, or that u to the 8 up. So we have u to the negative 8. So now with this expression we can easily find the antiderivatives. So we're going to go to step number 6 and find the antiderivative expression. So we're going to add 1 to each of those, so we get u to the negative 6, and to counteract, when we find the derivative, we're going to have to write negative 1/6 in front of that, and minus u to the negative 7th, and it looks like we're going to get positive 6/7 here maybe, and then plus c. So you constantly have to find the derivative of this to see if you get back to that, to check your answer. And looks like it worked. So now we're going to go to step number 7, which is we're going to put x's back in there. So what was u? U was 6 plus x. So we have 6 plus x, and by the way, we can go back to the regular color ink. Step 5 was the unusual thing that we had to do there. So 6 plus x to the negative 6 plus 6/7 times 6 plus x to the negative 7th plus c. And remember, on this problem, we're not trying to find the value of a definite integral. We're just trying to find the family of antiderivative functions. So this next step is going to be our solution, our answer to this problem. So there you go, that's the antiderivative, or the family of antiderivative functions. Often it's referred to as the antiderivative, but technically it's a family of antiderivative functions. Okay, so let's double check, make sure we got everything right. Everything looks correct. Okay, so let's try another problem like that. We're going to find the family of antiderivatives, but we have a complicated expression, so we're going to need to use u substitution, and u is going to usually be equal to the inside function. And du is 4x cubed. We need to write the ornament, and then of course we need to solve for the ornament dx. So we get du over 4x cubed. And then we're going to write our integral. We're going to convert it we're going to convert from a dx to a du interval. And we're going to replace dx with what this equation says dx is equal to. And step 5 is where we're going to start to have some problems. So this x cubed and this x to the 7th, we can consider those, and we see that some of these x's are going to cancel out, but not all of them. So we're going to be left with x to the 4th power. So that's a problem. We used exponent rule number 2 to subtract the exponents because we're dividing the powers. So we're stuck. There's nothing we can really do. But let's take this equation and rewrite it. And then let's solve for x to the fourth power. So x to the fourth power is u plus 8. Just doing some basic algebra down there. So now we're going to replace that integral with pi over 4 times u plus 8 times square root u du. So you might say, well, this is no easier to integrate than this up here, but with this expression we can't really simplify it. We can't change the form much. We can't use distribution, but with this integral we actually can use distribution. Remember, square root u is the same thing as u to the 1/2 power, and we can use distribution. U to the 1/2 times u is u to the 3/2, and u to the 1/2 times 8 is 8u to the 1/2. So now, to avoid confusion, we probably should distribute that pi over 4 also. And pi over 4 times 8 is 2 pi. Ready to find the antiderivative, so in step 6 we're going to find the antiderivative of each term. So we're going to add 1 to the exponent, and I think we're going to have pi over 20 as a multiplier, because when we find the derivative we're going to bring down the 5/2 and multiply it into something to get pi over 4. So what would that be? Actually, it looks like it's going to be pi over 10. I did that kind of fast. So we have our term there, and then we're going to add 1 again, and we'll have 3/2 to the power. And looks like we're going to have 4 pi 4 pi over 3. So again, when we find the derivative, we're going to multiply 3/2 into something to give us 2 pi. And that should be 4 pi over 3 for x. And of course we have to add our c value. Okay, so now we have our antiderivative, or a family of antiderivative functions, and step 7 is to replace u with what we set u equal to, which is x to the 4th minus 8. And as usual, we can't leave our answers with fraction exponents, so we have to replace those expressions with the square root of x to the 4th minus 8 to the 5th power, and the square root of x to the 4th minus 8 to the 3rd power. So that should be our answer. Okay, so I want you to take pictures of these two problems, and I want you to attempt number 21. So remember, when you get to step 5, the x's aren't going to cancel out, so you'll have to do something different. So try 21. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, I want you to try number 22. Now again, if you haven't got a picture of these problems we did, make sure to get a picture of those. Number 20 will help you with number 22. So try 22, and when you come back, we'll do it together. Okay, we're back. So there you go. If you got that right, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2. And 3, 4, 5, 6, 7, 8, 9, 10. But don't go before you get your homework. Let's take a look at the homework. Here's screenshot number 1 of the homework, and screenshot number 2 of the homework, and screenshot number 3. These limits of integration are kind of hard to see, so I'll zoom in there. And next screenshot, and the last problem. But don't go before you get the answers to the homework. Here's the answers. So be sure to get that homework done completely, correctly, neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.